This is lesson 10 for year 13 physics on electromagnetism. This is the last lesson for electromagnetism, and this one has to do with transient current and voltage in an inductor in a DC circuit. Okay, so here's the diagram. So I've got an inductor, and this shows the resistance of the inductor. There's an ammeter to measure the circuit current. Here's your supply, and you can measure your supply voltage, and the switch can be connected either to X or to Y, or it can be in between, so it's kind of got three positions. Okay, so when the switch is at position X, the current starts to rise or it increases, and this changing current will have a changing flux, and that will induce a voltage in the inductor. And this induced voltage will oppose the increasing current, so it will act in the opposite direction to the source voltage. Eventually, the current stops increasing or changing, and it reaches a maximum value. When there is no longer any changing flux, the voltage across the inductor will become zero. So at switch on, that is when it is at position X, your current is an increasing current, and the rate at which the current increases at the start is a maximum, and then the rate of increase slows down as the current reaches a maximum. The voltage across the inductor will be the same as the supply voltage at the start, and it will fall and drop down to zero once the current is steady. Now the time constant for an inductor resistor circuit is given by tau equals L over R, okay, where L is self-inductance and it's measured in Henry. Now when the switch is in position Y, so it's disconnected from the battery, and the switch is like this at the moment, the current will start to fall. So once again, the changing current and hence a changing flux will be induced. It will induce a voltage across the inductor, but this time the direction of the induced voltage will be in the same direction as the current because it's trying to prevent it from falling. The time constant will still be tau equals L over R. Now there's a third situation. When the switch is between X and Y, there is an air gap, and so the circuit is no longer closed. The air resistance is extremely large, so the time constant becomes very small. The current falls to zero in a very short time, hence the rate of change of flux is very high, so the maximum induced voltage will be extremely high, much higher than the source voltage. Since the circuit is open and no longer closed, Kirchhoff's law will no longer apply, and hence another reason for a very high voltage, but this is a better argument. Now this is how spark plugs work. So this is just comparing at position Y, and when there is, as opposed to that, when it's between X and Y and there's an air gap. So the current falls in both cases, but the current falls gradually over here, so the time constant is bigger. Whereas over here the current rapidly falls to zero, so notice this gradient is much higher, and so the time constant is very small. The voltage across the inductor will equal to the supply voltage at the start when it's in position Y. However, when there's an air gap, the voltage across the inductor is much higher. It's extremely high, and again it drops down very quickly, so that's why it's a spark. Okay, so look at the gradients.